IP subnetting part 1. If you haven't looked at the bottom of the window yet, this video will take a little extra time because I'm going to fully walk through multiple examples of subnetting based on network requirements. 4 different ones to be exact, and then leave you with a bunch of practice to do on your own. Now, one of the things that I've found is the best way to teach subnetting is not just to start talking about the advanced pieces of it right away and say, oh, this is what subnetting does and binary addition and all that. It's more so to apply it to the real world. So you can see that we have 4 separate scenarios, 4 different network requirements that we're going to walk through one by one as we determine how to break a network into multiple subnetworks one by one. Let's get going. Let's start off with network scenario number 1. We have an organization. This organization has purchased a Class C address 216.21.5.0. So they've purchased that from the powers that be, the internet, and they now want to use it to address this network. And this is a picture of their network. Now, here's the trouble, and this is why we need subnetting. They purchased a Class C network, and let me just write it over here, 216.21.5.0. Now, when they bought that, it's a Class C network, so the subnet mask is this. And the question I have is, how many networks do they get from that? Well, looking at it, it's just one. We draw our line boundary right there, and 216.21.5 represents the one network they get. That's their network. And this over here represents the host. It goes from 0 to 255 maximum, where you can't use 0 and you can't use 255. You get everything in between. You can't use the first and last address from the network range. So we have 254 hosts on one network. Now look at their network diagram. How many networks do they need? Well, let's number them. 1, 2, 3, and a lot of people forget these, 4, and 5. Remember, every interface of a router is a network. So we need a network address or a subnetwork, a network, for every single one of these locations. Here's maybe an office with an Ethernet switch. Maybe that's in Arizona. We have an office across the WAN link to California. The WAN link to get there is considered a network, and the office itself. Then we have a WAN link over from California to Florida, which we have an office right here and the WAN link itself to get there. So we have one network that we purchased, but we need to break it into 5. So we know our network requirements now. Now, here are the 3 steps of subnetting. Before we start working through this, let me give you a little disclaimer. First off, I wrote our network requirements up here. This was our Class C subnet mask that we needed, and we know that we need 5 networks or subnetworks based on what we saw on the previous slide. Now, the disclaimer that I have is that there are more ways to subnet than there probably are grains of sand on the seashore. I mean, literally, even myself, over the 12 years of teaching that I've been in, have taught this probably 6 or 7 different ways. About 5 years ago, I came up with this little 3-step process that will work for just about any subnetting scenario you can throw at it, and you'll be able to figure out the answer. Now, the first time we work through this together, it's going to look a little weird. And you're going to go, I don't know about that. But I'm telling you, after about the 3rd or 4th example of this, you're going to start going, oh, I see how this is working. And between this and the following video, I hope to give you enough examples and practice that you can work on yourself so that you'll be able to master this skill and master it quickly. So, our first step in this subnetting scenario is to determine the number of networks and convert it to binary. We need to use the skill that we learned previously in the previous video of binary conversion. So we know that we need 5 networks. Let me write up our binary chart. 128, 64, 32, 16, 8, 4, 2, 1. So 5 as a binary number is nope, 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 nope. Yes, there's our first one, 4, 0, 1. So we know that 5 is 0, 0, 0, 0, 0, 5 zeros, 1, 0, 1. That's our binary equivalent. That's all there is to step 1. The second step is the big one. Reserve the bits in the subnet mask and find your increments. Now, I'm going to show you something, and I want to make sure that when you start working on this, you don't skip this step or this part of the step. It may seem tedious at first, but you will greatly appreciate this after a little bit. We need to write our original subnet mask right here in all binary. So 255.255.255.0 is class C. Now, what's 255 in binary? All ones. That's the biggest number we can have, right? So 8 ones dot, this is the whole subnet mask, 8 ones, 1, 2, 3, 4, 5, 6, 7, 8, dot, 8 more ones, 1, 2, 3, 4, 5, 6, 7, 8, dot, and now 0 in binary is just all zeros. 1, 2, 3, 4, 5, 6, 7, 8. Now I need to have you make a mental leap with me, a transition. We've been looking at subnet masks like this up till this point, and we've been looking at them in decimal format. Everywhere we see 255, we go, oh, well, that represents the network. So we know 216 represents part of the network. 255, oh, 21 is part of the network. So we've been relating 255 equals network, and wherever we see the 0, that represents the host. But here's the leap I need you to make. We need to start thinking in terms of binary. So can I say, wherever I see ones as binary numbers, that represents the network, and wherever I see zeros as binary numbers, that represents the host. Is that an okay leap to make? Good. So what the beauty of video recordings is I can say, good, we're all on the same page, and we are. So we have right here our 24 ones that represent the network and our 8 zeros. Now what's our goal here? Our goal is to create more networks, meaning we only have one network and I need to create more, 5 of them to be exact. Now how many bits does it take to get the number 5? 3 of them. 3 bits, right? You can't get the number 5 with any less than 3 bits. Now when I ask that question, I know you may have been thinking, well, 2 bits, right? Because there's only 2 ones there. But if you look at this, if you only have 2 bits, what's the biggest number you can get? 3, right? If 2 plus 1, you can't get the number 5. So I'm not looking when I ask that question for how many ones do I have. I literally want to know how many bits does it take to get the number 5, and that is 3 bits, 3 bits total. So transition that back over. Our goal in this step is to reserve the bits in the subnet mask and find your increment. So when I say reserve the bits in the mask, what I mean is I know that I can't get the number 5 with any less than 3 bits. And I know that network bits are ones. So what I need to do when I'm making this reservation is give myself 3 more network bits. So I pick up where the ones leave off and go 1, 2, 3. 0, 0, 0, 0, 0. Now, I know, you're looking at this going, whoa, wait a sec, that was a little weird. I'm not sure if I followed that the whole way. Don't worry, we'll get used to this as we go through it again and again and again. But let me just reiterate, our goal is to create more networks because we only have one. And we know that it takes 3 bits to get our 5 networks that we needed, and then partner that with we know that network bits are 1 bits. It doesn't really matter that 5 was 101. I'm looking for 3 more network bits. So with that in mind, I just add 3 more right where my network bits leave off, left to right, 1, 2, 3. At this point in the problem, we already know what our subnet mask will be for the entire organization. It is 255, convert this back to decimal, dot 255. That's what this one is, dot 255, that's the third one, that's what we had originally, dot, and then we need to convert this last octet right here back to decimal. Now, again, using those skills from before, if we line that back up to the binary chart that says we've got 128, 164, 132, 0, 0, 0, 0, 0. So if I wanted to find out what this right there is in a decimal number, I would just take 128 plus 64 plus 32. And that, if we add that all together, will be 224. So our subnet mask that we get for our entire organization is 255.255.255.224. Now that's fantastic. We know what every single PC, what every single router, what every single switch, every single device in our organization that is on the network will use this subnet mask. Woohoo! Do the happy dance, but we don't know what that means yet. Great, we've got a subnet mask. That's a key part of the equation, but we need to figure out what that subnet mask means, and that's the second half of step 2. It says reserve the bits in the subnet mask. We just did that, and find your increment. The increment, this is the other weird part, is going to be the lowest network bit that you have converted back to a decimal number. So look at our network bits. Right here, this is a 128, right? 64 in decimal. 32, that is our lowest network bit converted back to a decimal number, 32. That is our increment. So with that in mind, we can move to step 3, which says use the increment to find your network ranges. This is where the subnet mask becomes meaningful to us. So I just changed my pen color here. Step 3, I'm going to take what I started off with, meaning the address that I purchased, 216.21.5.0, and then just begin adding my increment. Now my increment right here, this 32, is in the 4th octet, so that's where I do my addition. 216.21.5.32. 216.21.5.64. You can see all I'm doing here is adding my increment, 216.21.5.96. That's 64 plus 32. And so on and so on and so on we go. What this is, when I'm looking at this, is the beginning of each network range. Now, all I have to do is fill in the end. What's the last IP address before I get to 216.21.5.32, which is this one right here? Well, it's not a trick question. 31. Just take one away from 32. Put this through. 216.21.5. Last IP address before 64 is 63. 216.21.5.95. And so on and so on and so on we would go down and down and down until we found enough network ranges to fit our organization. These are actual reality to us. Meaning, let me do a quick sketch of that network diagram. The network diagram that organization had looks something like this, where we had 3 different networks that we were trying to address. Now what I can do is I can start assigning these network ranges to that organization. This one will address, I think this was Arizona that I put, the Arizona router, and they will use that range for this network right here. You can see what we've done is sacrifice the total number of hosts we have, or to get more networks. We originally had 254 hosts with our Class C address up here, and now we've sacrificed that and said, well, I'll have less hosts, but more networks. The second network range can go ahead and address, I believe this was California down here, and the third network range will address Florida up there in the upper right-hand corner. I won't draw the arrow across just so it doesn't get too messy. The fourth network range would address the WAN link. And the fifth network range, I didn't go that far because I ran out of space down here, but the fifth network range would address that WAN link right there. Those are the network ranges that I can assign to the devices. I would then assign IP addresses from these ranges to the computers in Arizona. I'd assign IP address from this range to the computers in California. This is the meaning of subnetting. Breaking our one network into multiple networks. We've got our new subnet mask that we use and our network ranges that can be assigned to the different devices. With that in place, I know at this point it's like, okay, I'm seeing that, still a little fuzzy. Let's do another example. Let the adventure continue as we move into TCP/IP subnetting part 2. What we're going to do is build on the foundation that we laid in part 1, which was the 3 steps of subnetting based on the number of networks, as in we had the number of networks that we needed and figured out our subnets from there. Well, this video changes that scenario a little bit, flipping it on end and saying we're going to subnet based on the number of hosts rather than the number of networks. Now this assumes that you've gone through part one, so I'm not going to spend as much time reiterating the 3 steps, but I guarantee you that seeing this will not only help you with the scenarios we're presenting right here with these 4 different scenarios, but you'll also get a better feel for even the scenarios from part one, because it is the same 3 steps in a very similar process. So let's get going. I'd like to start things off by a network scenario that's very similar to the one that we started the previous video with so that you can see the differences. We have an organization that's purchased a Class C address, again 216.21.5.0, and would like to use it to create networks of up to 30 hosts each. So if you think back before, we were trying to work through this scenario based on creating 5 networks. 1, 2, 3, 4, 5. But this scenario says I would like to create networks of 30 hosts each. So they're more focused on the number of hosts per network rather than the number of networks. When working through a subnetting problem of this slant, the steps are nearly identical as before. Well, I should say the steps are identical. There's just a slight tweak as to what we're looking at. So step 1 was to determine the number of hosts and convert that to binary, just like we saw with the number of networks. Here's our Class C subnet that we purchased. We know that we're trying to find networks of 30 hosts per network, so that's our host. Number of hosts, 30. With that in mind, let's break that down using the binary 128, 64, 32, 16, 8, 4, 2, 1. Now, with these numbers in place, again, we realize that we're only after the number of bits. So we don't need to figure out the whole number, although I will just for this example. 16 plus 8, that's 24, plus 4, that's 28, plus 2 more, that's 30, and then we have a 0 for the 1. So the actual binary number for 30 is 0001111, But again, being after that we're only after the number of bits, we're really focused on it takes 5 bits to get the number 30. Step 2 is then to reserve the bits in the mask and find your increment. Here's where the slight tweak comes in. I'm going to take the original subnet mask, and we start off with a Class C example again, 255.255.255.0, and write that in all binary. So 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. I'll show you how to improve your speed on that in just a moment on the next scenario. So we're looking at this right now in terms of this is our original subnet mask, and we need to do subnetting. Now, in the previous video, we were focused on I need more network bits because I needed 5 networks or 30 networks or 100 networks or whatever the scenario said. I was more focused on getting networks than I was on how many hosts were on each one of those networks. In this style, we're more focused on how many hosts we're getting. And yes, we're going to be doing subnetting, otherwise we wouldn't be here in the first place. We want to break it into networks, but we're not as concerned with how many networks we get as we are with how many hosts can exist on each network. So when you're thinking of this, I want you to just say in your mind, whenever you see how many hosts per network, just kind of like save the whales, save the hosts. You can scream it out loud, whenever, wherever you want. Because what we're focused on is saving the hosts. 1, 2, 3, 4, 5 to be exact. Instead of working from left to right saying I need 5 more network bits, I'm saying I can't get the number 30. I can't get 30 hosts with any less than 5 bits. We know that the host bits are 0, so we're saving 5 of them. Save the host. You can say it out loud. Now, once we've saved the 5 host bits, the rest of them can become network bits. It can move over to the network side, the dark side of the force, because we're still doing subnetting. We still want to subnet, but we're now focused on how many hosts we get rather than the specific number of the networks. So with that in mind, that is the only difference. So here we go. Let's work through the subnet mask. Our new subnet mask is 255.255.255, and if we convert this one back to decimal, that will be .224. If we add up all those numbers, or if we were using the bit notation, that would be a /24 plus 3 more, /27. Our increment is the lowest network bit, which is a 32. That's our increment. Now we can find our network ranges. We started with 216.21.5.0, and then we just start adding 32. 216.21.5.32.5.64.96.128.160, and you can just keep going, far as down as you'd like to go. Fill in the end ranges. Last IP address before 32, 31. 464, 63. Now I'm really shorthand writing this right now just to save the time, but this is filling in the end range for each one of them. It goes from 216.21.5.0 through 216.21.5.31. Can't use the last one, can't use the first one, so we actually get 1 through 30 that are usable in between, which is exactly the number of hosts that we were looking for. Just how many subnets do we get? 2 to the power of, well, we introduced 3 more subnet bits. 2 to the power of 3 will end up being, this is 2 to the power of 0, 1, 2, 3. So we end up with 8 total subnets if we were to work this down the whole way. And if we were to do 2 to the power of 5, because there's 5 host bits that we saved, minus 2, that leaves us with 30 hosts per subnet. Now you might notice that I'm moving through these a little bit faster because we've seen the foundation of the previous video where I work through them step by step, working very slow, explaining everything as I go along. What I'd like to do here is not only, of course, introduce the new concept, but to get you faster at this as well, to move a little bit quicker through these scenarios. So if it seems like I'm going faster, I am. We have another scenario, same style. We've got network scenario number 2, Class C example. We have the network 195.520, and the organization is looking for 50 hosts per network. So let's start it off again. Determine the number of hosts and convert to binary. I'll write up our binary chart over here, 8, 4, 2, and 1. We have 50 hosts. So I look right here, no, no, yes. Our first one goes at 32, so I immediately know it takes 6 bits to get the number 50. Sorry, let me just change my font that I'm writing with so it's a little thicker so it looks a little neater. We've got 50 hosts equals 6 bits. Now, what we need to do is reserve the bits in the subnet mask and find our increment. So our original subnet mask is 255.255.255.0. I mentioned that I was going to show you a way to shorten this down as well. Once you're comfortable doing this, you can look at this and say, well, I can't really change the 255s, right? Because since this was a Class C address to start off with, I can't change the original subnet mask, meaning I can't move it backwards, otherwise it wouldn't be a Class C address. So the way I do this is I just think, okay, so that would be 24 ones, ... 1, 2, 3, 4, 5, 6, 7, 8 zeros. Because the zeros are really your playground. That's where you can work. You can't change the original 24, so you can just kind of jot those up there like that. Just quick shorthand instead of counting them all out. Now, you have to ask the question, are we creating more networks or saving the hosts? And you have to put your hand in the air when you do that. It's required. And we look, and it's after the number of hosts. It's 50 hosts per network. So we are saving the hosts. 1, 2, 3, 4, 5, 6 of them have been saved because we can't get the number 50 with any less than 6 bits. The other 2 host bits can change over to 1s so that we can do our subnetting process. Once we do that, we know that our subnet mask will be 255.255.255 dot, and we have 2 bits. If we add those together, that would be .192 is our decimal subnet mask, or a /26, which is the 24 original ones of the Class C plus 2 more that we just added when we did our subnetting, /26 mask. Our increment, boom, 64. Box, 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 box. That is our number that we can use to find our ranges. So we say 195.5.20.0. Just start adding 64 to the 4th octet because that's where we're at. 195.5.20.64.128.192, and if we add 64 to 192, we'll actually get 256. Now, immediately when you say that, and by the way, this is the same all the way down, I'm just shorthanding it here. When you see 256, you should immediately go, okay, bing, I must have reached the end of something right there. So I just start filling in the end range. We got 63, whoops, 127, 191, and this goes up to 255. There is no 256 because I'm done, meaning I've reached my 4 network ranges that this will give me. I'm done. You might remember from the previous video where we actually started carrying over to the next octet. Well, you can't do that here because you started with a class C address, meaning you can't change the original network that you were given. You've just subnetted into 4 networks. And if you look at that, 2 to the power of x being the subnet bits, so it'd just be 2 to the power of 2. That's 2 times 2 is 4. So that tells you you only get 4 network ranges with, it'd be 2 to the power of 6 minus 2, you actually end up with 62 hosts per subnet. Pretty cool, huh? Now, a lot of this stuff that I'm doing, like adding 64 plus 64 plus 64, just comes from doing this 100,000 times. As you do this again and again and again, you'll practice. You'll get used to seeing what typical subnet values are, to where you can just see the 2 bits and go, oh, that's 192. As a matter of fact, the longer you do this, I'm to the point in my subnetting where I've practiced this enough, and obviously teaching helps. So I'll tell you what, find a family relative and teach them how to subnet. They'll love you for it, and you'll learn it even better. But teaching this, I can just look at bits and say, oh, that's 192. It's kind of like, have you ever seen The Matrix, where the guy's looking at the matrix in an encoded format, and he said, I don't even see the code anymore. I see a guy, a girl walking, a blonde, a brunette, it's just, he stared at the code for so long, it kind of fried his brain. You will get to the point where your brain is fried, and you will master subnetting. Now, you might be noticing, as we're working through these, I am emphasizing speed. Let me take just a moment and tell you why. Speed in the real world is not as critical. It's not like you'll be walking into a job where they're like, subnet this now, you've got 30 seconds, and that's what you've got to do. I just know that a lot of you are preparing for the Cisco certification exams. And if you are getting ready for those, speed is of the essence. CCENT, CCNA, and even CCNP, just about anything you do in the Cisco world will have subnetting involved in it, and you'll have to do it and have to do it fast. So just to give you an idea of where we've come from, I'm always watching the clock when I'm recording to make sure that we don't get too long or too short or things like that. And when we first did the subnetting examples, when we were in the previous video, we were at about 11 to 14 minutes per problem as I was working through and explaining what I'm doing as I go. The 2 problems that we've done so far, the 2 scenarios, we've spent, the first one was 5 minutes and the last one was 4.5 minutes working through those. So my recommendation is when you're working through these, obviously you're not going to have a voice in your head, well maybe you will, but explaining it as you go, and you'll be able to write much faster. But I would gauge your time and try to aim somewhere between 2 to 3 minutes per problem when you get to one of these. That's when you know you've got it fast enough to prepare for the actual certification exam. All right. Network scenario number 3. We've got now a Class B network. I've changed it up a little bit. And someone was reading Cisco best practice documentation, and now it says, I need 500 hosts per subnet. That's what Cisco says it should be the maximum. So now we go with our 500. Write out our binary chart. 1, 2, 4, 8, 16, 32, 64, 128, but I know I must go further in order to get the number 500 because that's above 8 bits. So I go 256 is my next one, double that, and you've got 512, and immediately I can stop there because I've passed my 500. Now that's not where my first one goes. My first one goes right here because I can't subtract 512 from 500. So just by drawing my initial one, I can see that it's going to take 9 bits to get the number 500. Second step, reserve the bits in the mask and find your network range. So original subnet mask 255.255.0.0. We are going to write that in binary, which is 16 ones dot 1, 2, 3, 4, 5, 6, 7, 8, 8 zeros. You don't want to shortcut the zeros because that's really where you work. 8. So we've got our 16 zeros. Now, are we creating 500 networks or saving the hosts? Saving the hosts. Not only is it more fun to say, but it's more fun to do. We have 9 bits right to left. 1, 2, 3, 4, 5, 6, 7, 8, dot 9. We've crossed that octet boundary. The rest of them can become 1. 1, 2, 3, 4, 5, 6, 7. That was the rest of those bits that were in the third octet. So with that in mind, I can look and say my new subnet mask is 255.255.254.0 is that guy, or a /23. I just think of a class C address with all these being 1 is a /24, so we subtract 1. Our increment, circle that guy is 2 in decimal. So we look at what octet that increment is in. It's in the third octet. So I start down here with 150.5.0.0, and I'll increment in that third octet. 150.5.2.0, .5.4.0, 6.0, 8.0, and so on we go. The end range goes through 150.5.1.255. This goes through 150.5.3.255. This goes through 5.255, and so on. Oops, 255, and so on and so forth. We go down the way. If you were watching the clock on that previous network scenario number 3, it was 2 minutes, 54 seconds we took once I got out of my, once we started actually working on the problem. Pretty good. That's the kind of time frame you need to be looking at for these. All right, network scenario number 4. Class A address, we have 10,000 and need 100 hosts per network. So 100, how many bits does it take to get that number? 128, 64, 32, 16, 8, 4, 2, 1. Our first 1 goes right there, so immediately I know it is 7 bits. Step 2. Our original subnet mask was 255.0.0.0, which is 8 ones dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8. Can't really shortcut class A subnet masks. So we've got 24 zeros that we're working with. So with that in place, we know that we are needing 7 bits and that we're after the number of hosts. So save the hosts right to left. 1, 2, 3, 4, 5, 6, 7. 1. So that's our 8 bits of our last octet. What happens to all the rest of these bits? They change over to 1s. So we did quite a number of subnets when we went with this class A address. So we ended up going to 255.255.255 dot, and then the last octet is 128. Our increment is, circle that, 128. Happens to be the same as our subnet mask. So now, with our network ranges, we start with 10, 0, 0, 0. Now to find out where to increment, we need to look at where our increment is at. It's in the last octet over there. So I say 10.0.0.128. The fourth octet is where I increment. 10.0. Oh, stop right there. If I add 128 to 128, I'll get 256. I know that's not possible. So if I fill in the end ranges, I'll have 128 to 120, or 0 to 127 is the previous one. This goes up to, if the next one was 256, this would be 255. So again, do that. We did this in the previous video. Just kind of add the 1, carry it over to the next octet. We start with 1.0, 1.128, 2.0, 2.128, and so on and so forth. We go down the way. Fill in the end ranges. This goes through 10.1 or 10.0.1.127 through 10.0.1.255. Sorry, I was trying to beat the clock. I'm sorry, but that's how we're going to work this. Sorry for the extreme shorthand, but this is working through a Class A example, and we would keep on going, keep incrementing through all of the Class B and C octets. So if you wanted to find how many subnets you would have, it would be 2 to the power of, we converted 1, 8, 16. 2 to the power of 17. So that'd be 17 bits total. I had to think about that one. Will tell us how many networks you'll have. Thankfully, if you're preparing for the exam, they will never have a question asking you that kind of math without a calculator. So I'll do 2 to the power of 17 equals, 131,000 subnets are at our disposal when we subnet a Class A address like that. Excellent. At this point, you should be getting a little better feel for how this subnetting works. As I did in the previous video, I have an on your own section. It's essentially homework to work through 4 different examples of this time breaking into networks based on host requirements rather than network requirements. As I did for the previous video, working through these without having an answer to check yourself isn't very helpful. So I've typed up a little walkthrough for each one of these, essentially the 3 steps we've been working through so far, so that when you finish them, you can compare your answers to what I have. That's available off of nuggetlab.com, and just look for the CCENT pack of some sort. It'll be a zip file where you can download all of this paperwork. We've got, after this, one more style of subnetting to show you. And in my mind, it's the easiest, but it's the most common style that's out there. Let's talk about, before we get into the new style, where we've been so far. At this point, you should know how to subnet based on the number of networks. If you were given X number of networks, you can break apart addresses and break them into subnets that meet those requirements. And you should be able to do that for hosts. When somebody says, I need this many hosts per network, then you can work through that, save the hosts, and meet those requirements and come up with a subnet mask and network ranges to deliver. I hope this has been informative for you, and I'd like to thank you for viewing. All right, it's the final piece, IP subnetting part 3. And thankfully, this one's not that difficult at all. It's considered reverse engineering subnets. Up to this point, we've talked about how to subnet based on the number of networks, based on the number of hosts, and now we're going to look at working it backwards, reverse engineering subnets. Now, as I mentioned in the previous video, this is the most common style of subnetting you're going to find in both the real world and in the certification exam. It's essentially a type of subnetting that says, here's the answer, now work backwards. We'll finally wrap up the whole subnetting section by talking about the great exception to the rule, and I'll explain that once we get there. So let's get going with the reverse engineering. Here is a perfect example of reverse engineering a subnet problem. We have a host or a router or a switch on our network, and we look at it and get this IP address information. We see its IP address and we see its subnet mask, and we're faced with the question of, is this IP address even valid? What network range does it belong to? Or, what network is this part of? Is it on the same network as the other hosts that are plugged into the same switch and all that? All of these questions are honing in on reverse engineering, meaning we see the IP address and we see the subnet mask, and we want to know what network range that IP address belongs to. So when you're faced with a problem like this and you're trying to figure it out, we need to work backwards. And in my mind, it's a little easier than the ones we've been doing up till now, like the number of networks and the number of hosts. We don't have to do any of the conversion to binary of those numbers and reserving bits and so on, because we have the answer. This is the answer. Somebody figured out the subnet mask for this host way back when, and in that subnet mask lies the key. We want to know what increment was used when we figured this all out. Meaning this IP address right here belongs to a range, and the only way that we can know the network range is to reverse engineer this, work backwards, and figure out what was the increment. The way we do that is take the lowest subnet masked octet, or the non-255 subnet mask, and break it into binary. So 224 in binary, if we were to lay out our binary chart, 128, 64, 32, 16, 8, 4, 2, 1. 224 is actually 111, 0, 0, 0, 0, 0. Now you can subtract that out and work with it, but after you see these subnet mask values for so long, you start going, oh, that's 3 ones. Now, what increment was used with that subnet mask? Well, it's the lowest network bit that one, so it is 32. So 32 was the increment that they used when they found these network ranges. So we'll start where they had to start when this subnetting was reverse engineering. And when I say they, I mean the network designers or whoever planned the scheme. So we'll put 192.168.1.0 and just start adding 32. 32, 64, 96, 128. Now we could keep going, but we've passed the IP address. So we can work backwards and find out, oh, this is the network range that they came from, 192.168.1.96 through, 127. Now you can still see it. That's the network range that we're working through. Is this IP address valid? Absolutely not. At least not to be assigned to a host, because that is the last IP address in the range, which makes it the broadcast address, which the only way that you'd be able to figure that out is by doing reverse engineering and seeing the error of assigning that IP address to the host. Let's move on to scenario number 2. Once again, we have an IP address assigned to a PC, 172.16.68.65. We've got the subnet mask listed below, and a default gateway is assigned, 172.16.68.62. IP address down here of the default gateway is 172.16.68.62. Looks good. That's going to be the gateway the computer uses as it goes out. And we see the subnet mask of the default gateway is the same. Everything looks good, and maybe down here is the internet. Now, this scenario might be a typical test question. It might be a scenario in your network environment. Either way, the only way you're going to know if everything is kosher on here is by doing the reverse engineering. So once again, we'll look at the subnet mask because therein lies the key. We see 255, 255, 255, 240. If we were to break 240 into binary, I should just have a template that I paste up here of my binary numbers, but get used to writing them. 240 in binary is 11110000. So there's our binary value, which means our increment at some point must have been lowest binary value 16. So when the designers of the network put this together, they decided 16 was their increment. Well, let's figure it out and see if we can find what's wrong with this picture or if everything's right. We've got 172.16.68 zeros where we'll begin and just start adding 16. 16, 32, 48, 64, 80. If we add 16, and we're good. We've passed both those numbers. Now, before we look back at this scenario, you may wonder, well, isn't this a Class B network to start off with? Shouldn't you have started from 172.16.00? Well, I guess you could have, because whoever subnetted this out initially probably started there. But the catch is that when you're incrementing by these values, you're always going to loop back around. Meaning, if I started from 172.16.00 and started adding 16 in that fourth octet, I'd go all the way up to 256 and then go clink, 172.16.1.0. over here, and then we add up all the values to 256 and then go to 2.0. So the point is that you would eventually reach 68.0 by counting by 16. You just take a lot more paperwork to do it. So instead, we can just start from the 0 in the last octet where this network range would have started. And if you look, we passed both of these IP addresses. 65, well, that one shows up right here. And 62, that one shows up right here. So wait a sec, we have a major issue. This PC is assigned an IP address in a different network than its default gateway. It belongs to this network range, 172.16.68.64 through 79. That's where the PC is at. And the router is at the network range above it. That's a big problem. PCs, even if they're plugged into the same switch like this one is to the router, if that device is on a different network, it will not be able to reach it. It's not going to know that that device is reachable, because when it compares its subnet mask and ties this all together, the PC goes, wait a sec, my default gateway is not even on my network. It must be somewhere else, meaning I would need a default gateway to reach my default gateway if this is how it would all work out. So this would indicate a communication problem. This would be the breakdown. And now you can see why this is the most common style of subnetting, not only on the exam, because it's very easy to embed something like that into a much bigger question. A scenario might say, oh, PC A here can't access the internet. And there will be a bunch of other scenarios in here of routing tables and protocols and blah, blah, blah to try and throw you off. But really, they're just not on the same network at all. They're not in the same range. Same thing in the real world. You'll need to know if devices are not on the same network, because that's where you need a router between them in order for them to access each other. The way we would fix this is maybe over here the router's connected to another Ethernet network with some PCs, and over here maybe this IP address is assigned, the .62, but this interface would need to have an IP address from the same network range that this host belongs to. Maybe .49 would be valid for this one. So host A can reach it and get through that router to another network. That's what routers do, is bridge networks and connect them together. So at this point, we've seen all three styles of subnetting that you can have. Figured out based on the number of networks, based on the number of hosts, and reverse engineering. I want to mention one more document that I've created for this series, and that is also available on nuggetlab.com. I realize that, many of you have been going through the examples at the end of every chapter, and a lot of times it is good to just have some practical examples sitting in front of you that you can work off of without needing to go through the whole video to relearn the whole process. Let me show you what I mean, and this will make a little more sense. I've created a document. It's in PDF format. Let me see if I can shrink it down a little bit more. There we go. PDF format right on the website. It is subnetting examples. What I have is in a text document. There are three types of examples that I'll show. One based on the number of networks, one based on the number of hosts, or hosts per network or clients, and then also an example of how to reverse engineer it. So what I've got is, you can see subnetting style 1, subnetting based on the number of networks. And I tried to, as well as I could, walk through my thought process on paper when I'm working through these. Kind of like when I was talking through them in the videos, that's my thoughts. And this is kind of me writing my own thoughts. We've got a service router given this. You must break it into 20 subnets. So step 1, determine subnets and convert to binary. So there it is. Second step, reserve the bits in the mask and find the increment. And we can see the binary tells you how many bits. Your original subnet mask is this. So that's our original subnet mask in all binary. We must convert 5 of them to network bits. So you can see what I did was try and write what my thoughts were in paper. So you can always print this out and refer to it at any time. I did one, subnetting style 1 is an example based on the number of networks with a class C range. The second one is based on the number of networks or subnets with the class B range, because I wanted to give you a feel for each style. Class A is just like class B, so I didn't really include one of those. We have style number 2 right here based on a number of clients, and then example number 2 is based on a number of clients with a class B address. So I did a class C and a class B for each one of them. And then finally, I have subnetting style 3, which is given an IP address and subnet mask, find the network range. That's the reverse engineering that we just worked through, and that you've got a full example of how that works as well. So I really encourage you to download that, print it out, review it a couple times. It'll kind of solidify everything that we've been talking about in one place. There is one more thing that is in this document, and that's what I want to talk about right now. It is what I would call the great exception. At this point, you've probably seen enough examples to get a feel for how this works, meaning how the process of subnetting works. When I say, oh, we've got 30 hosts per network, and I say our first step is to break that into binary, the reason that I'm doing that and I'm converting 30 to binary is because I want to know just how many hosts per network I'm going to need. I think that's the number for 30. I was just doing that while I'm talking, and if that's right, I must be really good, but it's probably wrong. So my thought is that, the reason I have you break that into binary is because I need to know how many bits it takes to get the number 30, because that will tell us how many bits we need to carve out of our subnet mask or save the hosts in order to get an accurate answer. Now, the great exception is kind of related to this whole process and how binary works. Because binary begins counting from 0, these network values may throw off your calculations for the number of networks, and these values may throw off your calculations for the number of hosts. Let me take one of them. Let's say you've been given 200. Here, let me just clear a little room down here. You've been given the IP address 200.0.1.0, and the question says, well, break that into, let's do 16. Break that into 16 networks. Well, when you figure that out in binary, we would say, okay, there's no 128s, no 64s, no 32s, oh, 116, and everything else is 0. So we would say, okay, in that case, it would take 5 bits to get 16 networks. But we can actually get it with 4. 4 bits are what's only required to get 16 networks. And the reason that exception pops in there is because we started counting from 0. Meaning, what's the biggest number you can get with 15? Or, whoops, gave you the answer there. What's the biggest number you can get with 4 bits? Well, if we count them up, let me just write the binary values above. 128, 64, 32, 16, 8, 4, 2, and 1. The biggest number that we can get if we added up 8, 4, 2, and 1, that'd be 12, 14, 15, right? But remember, when we start counting in binary, we start with 0 through 15. So technically, we can get 16 values or 16 numbers with 4 bits, 0 through 15. And that's why anytime you land on one of these significant binary boundaries, like somebody says, well, give me 64 networks, and you put a 1 right there, well, you can actually get 64 with 6 bits rather than the 7 like it looks like it requires. Same thing happens in the host values. Says the following host values might throw off your calculations because let's say they said we want networks of 7 hosts per networks. Well, you figure that out and you go, okay, no 128s, no 64s, 32, 16, 8, oh, 4, that leaves us with 3, so 2, 1. That is 7 in binary. Well, when we're working with hosts, it says, well, we need, 3 different values, 3 bits to get the number 7 because 0, this way, hang on, now I'm messing with my own head. This is 1, 2, and 4 right there. So if we add them all up, that would be 0 through 7, if you will, because that's a 7 of total. So it says, well, 8 is the maximum number that you can get with 3 bits. Sorry, I don't know if that makes sense at all, but meaning when you have 3 bits, the biggest number you can get is 8 hosts. Now here's the trouble with the hosts. Anytime we're figuring out these calculations, we always have to subtract 2 because one of those hosts will be the broadcast, one of them will be the network. So when we're looking at this, it shows 0 through 7. Well, that gives us 8 total values that we can have, but if we subtract 2 from 8, we're left with 6. So while we wanted 7 hosts, that was our requirement, give me 7 hosts, this would only give you 6 total values once you subtracted the 2. We'd come up 1 short. So I don't need to get into all the technicalities of why this is the way it is. To play it safe, this is the rule, always subtract 1 when finding the number of networks. Meaning, if the problem or scenario that you're trying to solve says, I want you to figure out 128 networks, well, subtract 1 and figure it out for 127. Or if it's saying, I want you to figure out 30 networks, subtract 1 and figure out for 29. It will never hurt you to do this on whatever calculation you're trying to figure out. It will only help you because it will avoid all of these specialized scenarios. Chances are very slim that somebody's going to come up and say, hey, I want you to figure out how, give me a network range for 63 hosts per network. I mean, that's pretty weird that somebody would be looking for that value. But nonetheless, we can use this rule. Always subtract 1 when finding the number of networks. And to play it safe with the hosts, always add 1 when finding the number of hosts. So if they ask for 63 hosts, You know, because of this rule, you're going to come up one short, so just add one to the number. Say, well, I'll figure it out for 64. Someone says, I want 20 hosts. Add one and figure out for 21. It's going to end up with the same answer if it's not hitting this rule, or if it's hitting this rule, it may save you a miscalculation. So this is the great exception, and I fully described this in that document that I just showed you, probably a little more concise than the way I've explained it, because it's hard when you're trying to show the binary and how that works. But that's the only time the 3 steps will lead you in a little different direction, is if one of these values are chosen for the networks or one of these values are chosen for the hosts. With that, I will close the door on IP subnetting. That is the subnetting and the skill that you will need when you're working with anything in the Cisco world, because as a Cisco technician, you have become the network designer. Sure, just about every other certification, Microsoft, Novell, they all talk about subnetting, but you can kind of skate your way through it without really knowing what subnetting's about, because you don't usually deal with it in the Microsoft and Novell world. You usually are getting your IP addresses from the Cisco designer that figures out all the networks and divides them up on a map and so on. So it's not as critical to those technologies. In Cisco, you are the network architect, so you have to know how to figure out the subnets and reverse engineer them. So to hit the high points, 3 styles: networks, hosts, and reverse engineering. I would make sure that you are able to figure those out within a decent amount of time if you're planning on taking the certification exam. And the key to these subnetting systems are practice. I know, it's brutal, but that is the only way that this will get down in your own mind. So if you want, you can come up with many different scenarios for your own practice, or go on Google and type in subnetting. Be warned though, you will see 5,000 different methods of subnetting, and once you try and start mixing many of those methods into your mind, it can just get confusing. So just look online for examples, for some sample questions that you can work through. I hope this has been informative, and I'd like to thank you for viewing.